All right, so we're going to look at Boolean algebra, right? In the term of, let's look at the same question that we try to simplify. So we talk about the rules, right? So let's review that part. So these are the rules. We have identity law, right? Null. So identity is, like we said, when 1 is there, it's going to have x, right? When O is there, it's going to be 0 when it's null. But for all, when 0 is R, it's going to be x, and so on, right? So we go through that. Idempotent law, x equals x plus x is x. Inverse law, x prime is 0. Sometimes you see this x bar, like with the bar at the top, mean the same. X plus x bar is 1, right? That's inverse law. So now we also have more, right? So we look at the property now. We have commutative, which is xy equals yx, x plus y equals y plus x. We have associative, which is x times y first, and then z then equals to x times y and z, right? As well as the plus. So distributive, right? So we've seen that when x times x, we have x, so that we have x, and we have x times z and x times and y times x, and then y times z, right? But we see that y times x and x times z is going to be, we can factor out, and then we can simplify, right? So let's review that part again. So x plus y z equals to x plus y, x plus z. I wonder if I can draw this one. So first we said we talk about distributive, right? X times x, right? Plus what? X times z, right? Plus y times x plus y times z, right? So x we get x. We can depend on x, right? X times x. Now we see that we have common factor right there. So let me show you. This is common factor is x, right? Correct? So same as this common factor is y, right? So it's easier when I write out, right? So that's why we said x1 plus z, right? Because we can use this distributive law, right? Yeah, 1 plus z is going to be, so like or, we know that when it's 1, it's always 1, right? So that's why we have just x times 1, right? At that point. So as well as this part, we say y, we have a y, did I have it right?
Z plus YZ.
xz and yx, so this should be yx, right? Yx, because distributive, right? Y times x and y times z. So yx, and then we have common is what? X plus z, right? X xz yx yz, right? So when we have, so it's gonna be what? Plus yx again, right? Plus z. then we can do the same. I keep typing z, it's x. So then we have common again, which is x, right? 1 plus y. Is that correct?
Plus yx plus.
How do we get from there to the one below it?
Sorry. Actually, I should not do that yet, right? So I should just keep doing that, right? And then we see the common x again, right? Right, so that's going to be 1, right? So that's why we have x times 1 plus yz, which is x plus yz, right? So that's why we get this guy, right? For distributive law. So let's look at OR. So OR is simple, it's just x times y plus x times z, right? So those are the properties that we need to know, and then we also get to the property of absorption. Absorption is, we said, when x times x plus y equals x. So like we said, if you really look at, okay, let's review again, right? So let's assume, right, y, remember this is Boolean algebra, so either 0 or 1, right? So I assume y equals to 0, right? So meaning that x plus 0, right? We talk about absorption law, right? Equals to x. So absorption law is, we said that, right? So let's see, meaning that if I assume y equals to 0, meaning that this line just going to replace y with 0. So now go back to the rules that we see before. We said or is going to be depending on x, right? Plus is or, right? So meaning that x plus 0 equals to x, right? So, correct? Because x plus 0 equals to x, right? So meaning that x times x is also depending on x, right? Then it's x equals x, right? That's how we simplify down, right? So now, if I assume, do the same thing, assume y equals to 1, right? We talk about absorption, right? Absorption, make sure I say absorption law. So instead of 0, I'm going to say 1 now. So meaning that x plus 1, right? So x plus 1 is going to be always 1, right? Correct? Because or, right? So we've seen from the rules before too, if you're still confusing. So that means x times 1, which is x, right? So that's why we said this guy is always x, right? So that's absorption law. So same with the or, right? So this one is and, right? So let's look at or. So this is and. X plus xy equals to x. So Again, if I assume y equal to 0, right? Or actually, you can just factor, right? x1 plus y, right?
Mm-hmm.
Equals to x. And then 1 plus y is 1, because whenever you have or with 1, it's always 1. So that's why we have 1. So it's equals to x, right?
Mm-hmm.
X equals to x. So that's pretty much just proof that this is true, right? So that's why x or xy equals to x. De Morgan is pretty much just the opposite, right? If you are x and y, and there's going to be not x or not y. If you are x or y and the whole thing not, meaning that not x and not y, just the opposite, right? And double complement x not, so have x out. So those are pretty much the rules that we use for Boolean algebra, and then we start to look at expressions, right? So last time we were trying to simplify this guy, and we see that it's not easy, and that's pretty much the test that you have to go through. 2 unit tests you have to simplify. We're looking at that as a finalized, right? So this one we see that we try to simplify by factor, but we can, so that's why we try to put identity rule first, right? X plus x prime. The reason we use x plus x prime because we see x and x prime here. Then we can start to factor it, right? So if you can see, I have x plus x prime. Now we're going to make the distributive raw, right? So we have yzx and yzx prime. Then we can start to factor. That's why we bring x and x prime in front, right? And we group that this guy is xy group and this guy is x prime z group. And we want to say, hey, this guy has z in common, right? And this guy has y in common, right? So try to actually is try to look at common as xy in common. Okay. So this guy has xy in common, and this guy has x prime z in common, right? Then we can have 1 plus z and 1 plus y out. Because we try to eliminate the 1 plus z and 1 plus y, that's turned to be 1, right? So the goal is we try to eliminating something, right? So that's why we put identity in. Then we have xy plus x prime z, right? Now to do this way, this one way to simplify, right? Boolean algebra. We said we can also look at using kMAP. We call kMAP. Okay, so it should give you the same result. All right, so let's look at kMAP. So it's invented in, I guess, 1953. So from telecommunication engineer at Bell Labs, named Maurice Cano. So he used that to design a phone circuit. So it's a graphic way to visualize the Boolean expressions. Okay. Someone called kMAP, someone's called kMAP. It's a matrix. You have rows and columns. So before we going to use this, let's start the what's min term, right? So it said the minterm for a function having the input x and y are x prime y, x prime y, xy prime, and xy. I think this should be x prime y prime. Okay? X prime y, x prime y prime. Let me put it in. Okay. So let's take a look at this Boolean algebra. Let's try to simplify this with Boolean expressions that we just did. Let me just save this. Sometimes I prefer to use Notepad++ because it's easier to add a new text. Let me bring that up. All right. So we're going to try to simplify this, right? So how do we do that? We can factor x, right? That should be easy one, right? So we said fxy equals to xy plus xy prime. So we get x, we factor x out, we have a y plus y prime. So y plus y prime giving you what? 1, right? So we have x, right? All right. But this one said, okay, this is a minterm, right? So whenever you have prime, we're going to have it as 0 as input. Make sense? Because they're false, right? X prime. So x prime, y prime meaning 0 and 0. X prime, y 0, 1. Xy prime 1, 0. And xy is 1, 1. Okay? Now let's look at kMAP. So this is kMAP. So a kMAP has a cell for each minterm. See that? This could be x prime, y prime term, right? So this could be x prime, y, correct? When x is 0, y 0, so that's x prime, y prime, correct? So I just look at the previous one, right? This is 0, right? X prime, y prime, right? Right? And this is x prime, y, right? Make sense? Let's go back a little bit. We talked about this table, right? Right? But again, I just changed that table to, let me just copy. Can I really paste on Notepad++? No. Okay, let's use Word now. So we upgrading our text editor every time. Right? From Notepad to Notepad++ and now to Word. All right. All right, let's go down to that. So we talk about this table again, right? So let's compare, right? But again, this one happened to have minterm happen to have a O and O, that's why it's O, right? But it can represent in this term x prime, y prime when you don't know what x and y is. But when you substitute x and y, it's going to be 0, right? If x is 0, right? If y is 0, right? But we just want to say this is going to be a minterm part. Let's not talk about the result here yet, right? So let me start to draw then. So okay, finish up next. So this is x, this is y. Okay, so x, me increasing the size.
Yeah. Now you change it. Now you change.
All right, we got x, and then we want y. So this is gonna be y. All right, so now we try to create kmap, right? So the first part is gonna be 0. It's just like the same table that we've seen, right? But we just like that table. We know that this can be input part, right? It can be either 0 or 1, correct? So I'm going to make it as all the possible value of x inputs, right? And all the possible value of y inputs, right? It can be 0 or it can be 1, right? So we're constructing the kmap, right? Now, we know that this is going to be the midterm. This 4, right? So how to make it 4, just the grids here, right? Those are midterm. So we know that if we have two inputs, we can have two inputs is x and y. So it could be I0 or 1. And the possible value out is going to be 4, right? 2 to the 2, right? So that's why we have 4 midterms, right? So those are midterm. Now, let's come back to our notepad. So what is our midterm here? xy. Where's xy? When x is 1, y is 1, correct? Because it's not prime, right? So when x is 1, y is 1, where do we go? Right here, right? Then we got to enter 1 in there, okay? Now what's our next midterm? x1, y0, right? Where is it? Right there, right? x1 is and y0, right? That's right there. That's another midterm. Okay? And the rest parameter is 0, right? Okay? You can put 0 or you can just, yeah, not putting, let's assume 0, right? So that's how you construct the kmap. Now, the next step is we just finished constructing this. This like a graphical representation of your Boolean expressions. Make sense? So this guy equivalent to that image. If you understand midterm, right? Yes, question?
So for the kmap, we have, is it a list of every variable? Or do we? I mean,
Every input, right? X and
every
Y.
possible input for x and y. But what if we have? Can it only be 2?
It can be more.
Okay.
But now we start with just 2.
Okay.
Now, any question about graphical representation of Boolean expression with kmap? So when we see this picture, we know that expression. When we see this expression, we have this image. Right? It can be alternate. Now, we know that in Boolean algebra, we can simplify, right? With the rules that we just covered earlier. Same. In Kmap, we can simplify, but we have our own rules. Okay, let's look at the sum of the rule first. Yes.
So if our f of xy was xy plus x prime y, would the kmap have a 1 in the top left and a 0 in the bottom left?
Okay, so the question is, if my expression is different, then your Kmap should look different, depending on your mean term, right? So his question is, you said that, right? Okay, then the Kmap. Okay, let me save this, and then I'm going to just don't have to redo this, right? Just so I'm going to save as and change an image, right? All right, so what should it look like? X prime is 0 and y is 1. It should be there, right? Instead of 0, it should be 1 right there, right? Oh. All right. It's not easy to be a professional paint editors. All right, so I'm gonna do that and just hit 1. Okay. And this has to be. All right, so let me just change that to 0. See if we can get this time. There you go. Nope. All right, so that's pretty much what it is, right? Now let's learn how to simplify, right? So now let's simplify this guy then. Can you simplify this guy with Boolean expression with the new equation first, the new Boolean expression first? So we know the factor is y, right? So y is a common factor, correct? So we gotta take x plus which is gonna be 1, right? So the answer is gonna be y. Now let me show you the rules of Kmap when you simplify. So Kmap said you have to find a group of even number. So let's say, can you find a group of even number? We talk about even group of ones. And it has to be even number. The member of one the group has to be even. So meaning that if I have to find a group of this guy, I'm going to say this is one group here, right? And now after you have this one group, you're going to look at, oh, it's y. So we just finished simplify it, xy. Correct? Because this group has the same thing, which is 1, which is y. So that's how you simplify it. Isn't it easy? Okay, let me repeat one more time. You have to find a group, and the group always has to be even number. You cannot have a group of 1. That's not even, right? So that's why I have to have a group of 2. That's even. And after you have the group, then look at what is in common. Y. This is not common, right? So that means you simplify to this Boolean expression equals y. Question?
I mean, that works fine in a small kmap like this.
Okay, let's try with this small kmap again. Same, the first expression.
Yeah.
A group of even number. Done.
Yeah.
Right? X. Alright, so now let's make it more complicated.
I'm looking at the Wikipedia page. I'm looking at this.
Yeah.
Confusing.
So, yeah, are you confusing so far then?
I get what you have for.
Because my job is to make sure you're not confusing.
I get how you.
Right.
The
Let's go back to the complicated question that we used to do. And you agree this is not easy. Remember that question that we tried to do? This guy. Alright. So we're gonna try with this. Now we start to do our kmap. Alright, so let's review kmap again. Now this is two inputs, right? We have minterms, 4 minterms. Now this expression has how many inputs? 3. So how many minterms you expected? 2 to the power of 3. I mean, pretty much all the possibility, right? So these are all of them, right? See that? So when all of them x bar, y bar, z bar, x bar, y bar, z, and x bar, y, z1. I mean, and so on until x, y, and z. Okay, I don't have to say it out. Everything you understand. All the possibility of inputs, pretty much those are minterms, right? So minterm is nothing beside all the possibility of your inputs, correct? Alright, so let's construct kmap together. So that's the minterm with 2 inputs. Now there's the minterm with 3 inputs, right? So let's look at kmap now. So this is for 2 inputs. So for 3 inputs, there's no restriction on the order of x, y, and z. Like, if you look at the image before, x can be here, x can be here, y can be here. It doesn't matter. It's going to give you the same answer. Okay? So, because at the end of the day, when you circle, it's just look at this. Make sense? So now we will construct a new kmap. Oops. Alright, so this kmap is going to be 3 input, right?
All the combinations.
Alright, so the first one I'm going to make it as, we have x, y, and z, so this is x. Like I said, you can have x and y, but you have to make it longer. Now I'm going to make y and z on this part. Okay, 3 inputs. You have 4, it's going to be x, y, z, and w, right? And so on, right? So, what are the possible value of x? 0 and 1. Good. What's the possible value of y and z? That's right. 0, 0. Okay. And then next one is 0, 1, right? I can just use that actually. 0, 1, and what else? 1, 0, and 1, 1. Oh, I forget to bold it.
It's too late.
That's why.
This is fine.
It's okay. It's fine.
That's hard to use paint. You have question?
Oh, I'm wondering why is it 0, 1 and 1, 0 since they are n. So both of them is 0. Okay? Outcome both is 0 since it's an and situation with y and z.
A 1, Z? Yeah, it's just next to each other inputs, right? It's just like the tabular here, right? That we talk about this guy, right? All the possible values.
So basically,
I'm construct from here, right? X could be 0, Y can be 0, 0, right? Y and Z here, right? So that's mean term is X bar, Y bar, and Z bar right there.
That's not an equation. That's a label of the axis.
Right. This represents this whole table, right? Mean term, right? Now, once we get this, then we're ready to do the simplify expression right here, right? All right, guys. What happened to Z here, huh? We have Z, right? So let's maybe exercise a little bit with one example first before we go to that one. So let's find a question with right there, because I want to see with Z first before we go without Z. Okay, make it easy question first, and let's do both. So we can take this equation, simplify with Boolean algebra first. Okay, let's do that together. Let's do both ways. So your class exercise, you have to do both. Your assignments say that do with Boolean expression and do with kMAP. Then you can practice both. All right, let's do this together.
Yeah. The parentheses.
Okay, so we say we want to take out all Z, right? And factor that, right? Anything else in common? In common is X here, right? And this one is in common is X prime, right? That looks right. Now we know Y prime Y, what do you get? 1, right? Then we have X prime times 1 inside the parentheses, right? So let me bring Z in front then. Plus X 1. which is gonna get
Z.
Z, right? Because x prime plus x is gonna be Z. Easy.
That's good enough.
All right, so let's do a kmap. So find the midterm. 001, right? But by the way, there's a problem about this guy.
Yeah.
Whenever you put this, you allow to have one change, meaning 00, you connect O here, right? And the difference is 1,
Mhm.
right?
Yeah.
One O, that's a problem. Because this change 0 to 1 and 1 to 0. This is two changes. Make sense? Like this from 0 stays 0. 0 to 1, one change is fine. 0, 1 to 1, 0, no. Because the first digit change 0 to 1 and the second digit change 1 to 0. You have two changes. Then this guy, we have to make it 1, 1, right? Instead,
And
right?
erase the one on the right as well.
Right. Or let's see if I can move this guy.
Paint master.
And then now let's see, this is only one change, right? 0 to 1 and 1 stay the same, which is fine, right? And then the last one is 1, 0 is also one change, right? I mean, that's the rule of kMAP.
Because otherwise all those things are next to each other.
Because we want to group even and it has to be neighbor. Otherwise, it's going to be two separate groups. Right? Now let's do it. X bar, Y bar, and Z. 001, right? Where's 001? 001. 1. And next one is what? 100, right? 100, correct? Because in the same order, right? No, I'm sorry, 011 because X bar, right? 011, which is right here, right? 011, right? All right, so what's the next one? 101. Just down there, right? Okay, so and 111. So right there. See that if I don't move it, we're gonna have two separate. And when we group, we have to group the group of one that adjacent, right? So now, and the group of even numbers, right? So the big group is 4. So now we have in one group, which is this guy. A group of, yeah, like circle it, make them all together in one group. And now you find a common. What's in common? X and Y is not in common, 01, right? Y is not in common because 01, right? But the one is common is Z, 1, 1. So simplify to Z. That's how you use kMAP to simplify. 0, Z bar, yeah, Z naught, or Z prime.
I understand why grouping is important for the graphical representation of life, because they're all in a single group. But theoretically, like even if they're separated, the consistencies between the min terms are still the same. It doesn't matter if it's separated horizontally or not, because you can still see that x is either 0 or 1 and y is either 0 or 1. And that c is the consistent term, not necessarily that. Like, is there an example where they have to be beside each other? Because in this one, they don't necessarily have to be beside each other.
Yeah, I mean, it depends on the equation here, right? So, like, if I happen to have like that, then you have to simplify differently now, right? And they're not going to be beside each other anymore. Which we have a lot of exercises for you to practice. Okay, then you need to practice that, right? For our homework. At the back of your textbook, we have that. So now we have the answer for that. Let's see, this is another one, right? And this is another example that. So let's look at this one. We have x bar, y bar, z bar. That's mean 0, right? Which is that one, right? And then 001, right? And 011, 011, right? This is 011. 011 should be right there, right? And then 101, right? No, 010, right? 010 is right there, right? And then 100, and then 110, right? Now, when you look at kMAP, so this is important, okay? So pay attention. It's not a flat 2D, it's like a ball 3D. Meaning that this one, this side connect to this side. This side, so right connect to the left, bottom connect to the top. It's like ball. So that means you're gonna group in a group of adjacents. So that means this one adjacent to this one. This one adjacent to this one and this one and this one and this one too. Like you can make an adjacent corner too. Or you can make a group like that too. Like if you look at the slide and make group like that, right? Because it's like ball, it's not flat. It's like 3D, right? So that's why you can make group like that, group like of even number, right? We can make two groups and it can be intercept because we want the largest group. Like this is adjacent by 4, then we make the largest group. Yeah. So those are the rules, right? Even, large, just, adjacent. So now after that we simplify by we look at what's in common on the green and the pink. So let's look at pink. X is not, right? Because 0 and 1, right? Y is not because 0 and 1, but Z prime because 0 Z, right? So it's Z prime right there for the pink. And for the green is X prime. So we can simplify the previous expression to X prime and Z prime with that big expressions, right? With kMAP.
We had something like an or out of a kMAP, like x naught or
Oh. So you talk about this is we call the sum of product and the product of sum. So this is a sum of product, right? So we look at these are the products, and this is the sum of product, right? But his question is, we can have x plus y, right? X bar plus y bar plus z bar times x bar plus y bar plus z times x bar plus y plus z times and so on. So that's called the product of sum.
So if we came up with that, we have for like time. The result would have to be multiplied.
But this one we look at multiply, right? And product of sum. Sum of product, I mean, right? Because these are our mean term. We didn't have all as the mean term. And this is for 4 variables mean term. You can do W, X, Y, and Z now, right? W is another input. And this is an example of expressions, Boolean expressions, that you can have those mean term on those group. Now let's look at how we're going to group it. We can have a group of 4 here and here, right? And we can have actually a group of 4 at each corner, right? Like that, and then a group of 2. That's the largest group, right? That is Jansen's, right? And then we can simplify that to, let's say, the corner one, let's look at is O. No, W is not in common because, right? X 0, 0. Okay, X is in common for the corner, right? So we have X bar, right? And then Y is not, right? 0 and 1. But Z bar is, right? So that's why we have X bar, Z bar. So we have X bar, Z bar, right? So now let's look at the pink. In common is what? W is not, X is, right? So X bar, right? Is that right? 0 and 0, right? Okay, X bar, and then let's look at Y. Is Y the same? Yes, Y bar, right? So this is wrong. It has to be X bar and Y bar, right? See that, right? X bar and Y bar. This one is W bar, right? And Y and Z bar. Okay? Question? Now, sometimes it's possible that you can run into this situation. You can have more than, right? This is the same thing, but you can have 4 of this. You can have 2 of this, right? And 2 of this. It's possible, right? Right, when you want to keep the group as large as possible.
Graph on the left, correct me if I'm wrong, but wouldn't the pink be a group of 3?
No, 2.
It has to be even.
Yeah.
This is just, we look at the one in the rectangle. This is just like index, letter index. They are pretty much the same thing. So let's try to write the expression for this too. So what should be the first one? This is x, y, z, and w, right? So in common, like we see, the green is y naught and z naught, right? So pink, w naught x, right? What else? Is y in common? No, but z naught, right? Correct? And blue, yz. What else? W naught too, right? Yeah, because you see that the smaller the group is, the more variables has to be involved, right? The bigger the group is, the smaller variable is going to be, right? So, and this expression you cannot simplify further, right? Right? The most you can do is just factor the b bar, but it didn't do anything for the z bar, huh? Say again.
Which one was pink?
Pink is the middle one.
Oh, okay.
Is that correct? So let's do the one on the right. So y naught z naught, right? Plus let's do pink first. Pink is going to be w naught x, right? And y, right? And green, w naught yz, right? I mean, if you want to order by the alphabets, so we can do that. X, Y, W, right? X, Z. Yeah, W should come first. So I order right then. Right, W should come first. All right, so so meaning that we can simplify into either one of this. Questions?
Is that pink? Y and Z are and it's the y equals Z
Yeah, it looks like it should, right? Because when it's come like this, y equal to z prime.
So
But this one said we cannot simplify further from the chart here, right? So it meaning that whatever we can either take y or z prime as the input, it will give you the same output. So meaning by this. But it doesn't mean that y and z prime is going to be equivalent, right? So don't care. So real circuit don't always need to have an output defined for every possible input. For example, some calculator display consists of 7-segment LED. So let's look at what 7 segment digits. So if you look at your digital clock, that is 7 segments. They use 7 segments. So you probably have to do this in your test. You're going to design a circuit for 7 segments. 1, 2, 3, 4, 5, 6, 7. See that? Represented by letter A, B, C, D, E, F, G. Those are output, right? So in order to get that, these LEDs can display. So do you see those represent the LEDs? LED is that, if you don't know what's LEDs, the light like that. It's cost 49 cents to get it. So expensive. Those are LEDs. You see some light bulb that pretty much your flashlight they use LED now to make the lights, right? Yeah, that's LEDs. That's LEDs make lights. So meaning that if you have 7 LEDs lining up like that, then you can create numbers. That's why you can create digital clock. Right? Digital clock always like that, right? And then you can do all the numbers, decimal numbers, right? Depending on you activate A, B, C, D, E, F, that's 0, right? If you activate B and C, that's 1, right? Make the lights, right? Right, these LEDs can display 2 to the 7 minus 1 patterns, but you only need 10. So you have 7, right? Which is a lot, right? 2 to the 7, but you only need 10 outputs. So the rest, I don't care. So if a circuit is designed so that a particular set of inputs can never happen, we call this set of inputs don't care. It can be 0, it can be 1. It's not going to affect my output, right? So that's called don't care, right? They are very useful or helpful for Kmap circuit simplification because we can make it as group of 1. We have bigger group. So X are the don't care. Meaning that it can be 0, it can be 1, right? And we are free to include that as part of our group to make it 1. We have bigger group to simplify the circuit. We have this, right? Make it bigger, right? And this, right? That's so from here we have, we actually just enough that one, right? So we simplify to W prime Y prime plus YZ, right? It should be X prime, right? Correct? W prime X prime, right? Make sense?
So we didn't care about
We don't care about those midterm. And this is another scenario that I try to show you, right? B prime Z plus YZ. Yes.
What if instead of the one being at, what if we had the one somewhere else? Can it be somewhere else? Or like if it was in a grouping that was in itself with an X or with a don't care value? So if instead of that, Y not Z and not W not X, we had the one per. What if due to the don't care values, we had a value that we do care about paired up with a don't care value? Like if we had a 1 in the bottom left corner.
Okay. 1 here.
Yeah, it would be that, and it was, let's say it was paired up with the don't care value above it. Can that happen?
Yes.
Okay.
Then we group it.
All right. So the grouping still stands even if we don't have if we have a don't care.
Just doesn't show up in the equation.
Right. I'm just making sure.
It still show, right? If you have 1 there.
Yeah.
Then you circle this, and it's gonna be plus XZ, X bar Y Z bar, right? X prime Z prime.
So we make the groupings before. Well, when we make the groupings, we care about the don't care values.
Yes.
But not when we put them into the equation. Or when we make
We have to use that, right? We use that to simplify it.
Yeah.
Don't care used to simplify. Otherwise, it's gonna be W X prime Y prime Z prime.
Yeah.
But when we use don't care, then it's simplified to
So
W Y prime Z prime, right? That's why don't care is good for this. I said, yeah, this we may see like the same question that we see that we don't care, right? Even it looks different here, right? At a simplified form. However, the value for which they differ are the inputs for which we have don't care conditions. Right? Y prime W prime Z is what? W prime is pretty much just the group that with the don't care condition, right? As well as this one, right? So that's why that.
use don't care conditions to do that when we can just say w prime x prime z and shrink the panc by 2 or by 1 vertically. Like if we just wrap the 2 ones in the middle,
then we're gonna get w prime, right?
We get w prime
X prime z, yeah.
plus yz. So it just shortens it when you write it out, but isn't that more efficient? Or is it not?
Because you pretty much just reduce one more n, right? You simplify your circuit, make it smaller. If you have one more x prime right there, you have to add n and not 2 more gates, right? So that's the point of simplification, right?
How do the don't care conditions get handled? Like, how are they ignored?
They're inputs which you can't get by the circuit.
Okay.
So you can't input w not x, not y, and z. It's just an input that can't go in the circuit.
Yeah.
Oh, no.
You no longer need those inputs, right? You see, you don't need x in here anymore. And that's save a lot of, right? You don't care about those input too. Yeah, x no longer here. All right, so that's the end of kmap. All right, so